So, welcome to module 2.2. In this module, we will look at signed number representation, or what we call as signed binary number representation. So, how do you represent a signed integer, say +2, +215, -3216. So, we have something called a sign prefixed. So, the logical way of communicating to a computer the sign of a number is to have the most significant bit. Here also we have had the most significant position, right. Plus is plus 215, which is the most significant digit, 2 is the most significant digit, and we had the plus after the most significant digit. Similarly, -3216, 3 is the most significant digit, and you had the minus just before the most significant digit. So, the best way to tell a computer that as integer is negative or positive is to use the most significant bit for this purpose. If the bit is 1, then it is negative. If the most significant bit is 0, I will call it MSB. If the most significant bit is 0, then the thing is positive. If the most significant bit is 1, then it is negative. If it is 0, then it is positive. So, this is how basically we work, and this is now let us go and see how we are going to do a signed number representation. Now, let us just see this. Let me say that we have 0, 1, 2, 3, -1, -2, -3. Suppose I say I have 3 bits. Suppose I say I have 3 bits to represent any number, and suppose I want to represent signed numbers. That means, as mentioned in the previous slide, page, the first bit will be used for sign. So, remaining there will be 2 bits. So, let me call it bit 2, bit 1 and bit 0. Bit 2 will represent sign. So, bit 1 and bit 0 will represent the value, right. So, if I say 0, 0, 1, 0 means plus, this 0, 1 is nothing but 0 into 2 power 1 plus 1 into 2 power 0. So, this will represent plus 1. Suppose say 0, 1, 1, 0 means plus, this 1, 1 will be 1 into 2 power 1 plus 1 into 2 power 0, which is 2 plus 1, 3. So, this will represent plus 3, this will represent plus 1, and so on. Suppose I put 1, 1, 1, then this will represent, this can represent, in some sense this can represent -3 also, right. So, now we will now look at what we call as the we will call this as 2's complement representation. You would have learned this in your introduction to programming course, but I am quickly giving a recap of this 2's complement representation. Using this 2's complement representation, with let us take 3 bits for example, we can represent this range, that is -4 to +3, and let me tell you how this is going to happen. So, let us see 3 bits all combinations I am writing 0 0 0 0 0 1 0 1 0 0 1 1. One zero zero, 101, 110, 111. And note that by our theory of these 4 fellows should represent negative numbers, because what, their first digit is 1, the most significant bit here is 1, while these fellows should represent positive numbers. Why? Because the most significant digit in this case is 0, which is positive. So, I can represent 4 positive numbers and 4 negative numbers, the total 8 combinations I have. Okay. Now, let us name this. So, this is positive is very easy. So, this is 0, this is 1, this is 2, this is 3, right. Now, let us start so this is a wheel which starts from 0 0 0 to 1 1 1 again back, and please, so let us model addition. And so, if I have signed numbers, then addition can essentially become subtraction. For example, suppose I say plus 3 plus minus 2 is nothing but 3 minus 2, which is subtraction, right. So, the moment I have signed numbers, adding 2 signed number of opposite sign essentially implies subtraction. Here I am adding plus 3 to minus 2. So, essentially adding 2 numbers of opposite sign, it essentially boils down to subtraction. Same thing can happen here. So, the way we are doing this is 0 1 2 3, but then we will go and make this as minus 1, minus 2, minus 3 and minus 4, right. Now, the good thing here is that if I want to add some number a with b, I go to a and move b positions clockwise. Okay. So, when I want to subtract say b from a, I go to the position of a and move b positions anti-clockwise. Move b positions anti-clockwise from a, move b positions clockwise from a, clockwise from a. So, this is how we basically look at this. So, for example, let me say I want to add 1 plus 2. So, I go to 1 and add 2 positions. So, I get 3. So, 0 0 1 plus 0 1 0, if I add, I get 0 plus 1 is 1, 1 plus 0 0 1 plus 0, 0 0 1 plus 2, 0 0 1 plus 0 1 0, 1 plus 0 is 1, 1 plus 0 is 1, 0 1 1, I get this, right. Look at the other way. Suppose I want to subtract 3 minus 1, I go to 3 and move anti-clockwise one step, right, and I get 2. So, your subtraction becomes anti-clockwise, your addition becomes clockwise. So, let us say I want to subtract 1 minus 3, I go to 1 and move 3 steps anti-clockwise, 1 2 3, I get minus 2, right. So, 1 minus 3 is minus 2. So, that is what you get here. Okay. So, this circular representation of the number line, right, right, is basically helps you visualize addition and subtraction as clockwise and anti-clockwise movements respectively. Now, what is interesting here is, now let us see this. Suppose I have 1 minus 3, right. So, I am at 1 and I am moving 3 steps backward, right. So, I am moving 3 steps backward, 1, 2, 3. So, on a circle of size 8, moving 3 steps anti-clockwise is equal to moving 5 steps clockwise, right. Moving 3 steps anti-clockwise is equal to moving 5 steps clockwise. Let us see what happens if I move 5 steps clockwise, I get back to the same position. Right. Now, you understand. So, instead of moving anti-clockwise, I can move 5 steps clockwise and I get the same. Now, what is the binary representation of minus 3? 101. And what is 101? In decimal it is 5, right. So, if 1 is represented as 001 and minus 3 is represented as 101, right. Now, adding these 3, adding these 2, just add these 2, because from 1 subtracting 3 is moving 3 steps anti-clockwise, that is equivalent to moving 5 steps clockwise. And what is clockwise here? Clockwise means addition. So, instead of subtracting 3 like this, I add 5 here. So, that is what I am trying to do. So, 001 plus 101 will give me 1 plus 1 is 0 with a carry 1. So, I get 110. And what is 110? 110 in our representation is minus 2, right. So, what has happened here is the subtraction has actually become addition. So, if your numbers are represented in 2's complement notation as we have seen here, then what will essentially happen is there is nothing called subtraction, everything is addition, and you will get an answer accordingly. So, that demonstration we have done here. If I want to subtract 1 from 3, I add 5 to 1 to basically get 110, and that 110, the representation for that is minus 2. So, if I store the integers in this format, what we call as this 2's complement format, then basically you need not have a separate subtractor, everything can basically land up as addition, right. So, this is a very quick introduction to 2's complement arithmetic. We will see how we can generate these 2's complement arithmetic in the next module. Nevertheless, I suggest that if you are if you have not studied 2's complement, or you forgot what you have studied, what you have learnt in your introduction to programming course or first year course where this should be taught in any curriculum, then I strongly suggest that you go to any Wikipedia page. There are many introductions to 2's complement. Just have a look, a 5-minute read will basically brush you up in addition to what I have covered here. We will now go to the next module where we will understand, given a number, how to generate its 2's complement. We will see from an hardware perspective. Thank you.